Hello, good morning. I'm going to talk about a specific case of digital twinning, and it sounds too specific, but it actually has a general sort of like the methodology we developed is very general. So you'll see that by the end of the talk. So I'm going to talk about digital twin of manufacturing of advanced ceramics. I'm Jingzhe from University of Leicester, and here are the team working with me. We have a digital twin lab at Leicester, funded by UKRI. And centering manufacturing ceramics, you probably have we all have some lovely sort of ceramic product, but something we like, something we use. But actually, ceramics, advanced ceramics, are also used in industry, and we don't know them very much because they are all hidden. But when you use ceramics in the industrial or in a machine, that's because you have no choice. And therefore, those ceramic parts are critical to the performance of the machine. So I'm just giving you an example here. This is a ceramic matrix ceramic composite, and it's a large heat shield, and is manufactured through using a kiln. So the challenge of making these things, and as I say, this is a big part. It's not like a small pieces anymore. The things are 1.5 meters tall. And if you are not careful, the way we make ceramics, we form them, it's a forming, then we sinter them, fire them. And that step, if you're not careful, you end up with a distorted shape. And then because this is ceramics, it's very hard, to correct any mistake at that stage. So you can either reject them, you can say that some of the rejection rate are 50%, or you have to do machining. And again, that's very expensive and something you don't like to do. But people are forced to do that in the current manufacturing process. So really, what we're worried about is this manufacturing process, is this firing process. So we want to control that distortion and shrinkage. So I just want to show you the challenge. I took this picture. So the picture on the left is the original part, which is before firing. It's like this is aluminum, and once you fire it, you end up with a perfect, very strong and solid ceramic piece of ceramic. They are very strong, and you can see the shrinkage. So the material shrinks a lot. So if you don't control it well, you'll be in trouble. So let me just show you a simulation of that sintering shrinkage. So actually, you can do finite element models and run the simulation. And this is the case which I shown here. This is the ceramic panel. I can't show you the real part because that's industrial sensitive data, but I can show you the mathematical model. And if you're not careful, you end up with something like that, then you will be in trouble. And then it's very obvious. So people have been trying, I myself, we've been trying to do method modeling for this kind of deformation, and but there is a challenge there, and the challenge is whenever you do a computer simulation, you need good data. People always say you put garbage in, you get garbage out. So you need real sort of material data. And the material data, one problem with this kind of manufacturing of ceramic is that the material data is very, very sensitive to the actual material you're using. So here is a plot of a particular material parameter you need to plug in the model in order to do the simulation. And the vertical axis is the value of the parameter. The horizontal axis is the density of the material. And if you look at any particular density, particularly when they reach full density or early stages in a loose density, you can see that the material parameter varies hugely. So that is the problem. And which one do you use in this simulation? So the obvious solution to this is to do a digital twin. The digital twin, I mean, we all know what digital twin is. The basic idea is that we have a mathematical model, and then normally, in this case, is a finite element model. Normally, you do finite element prediction. You have data, you plug in, you provide your boundary condition, everything. You run your simulation, and you calculate the deformation, or cracking, or microstructure, or whatever you like. And the model has been developed over many years and decades to do that, and that's all there. And the problem I have that is the parameter we plug in this model are uncertain. So what we want to do in the digital twin strategy, we want to collect data in the manufacturing process. We call in-process measurement. If we can collect data from manufacturing process, if we can do back propagation, we can work the backward rather than sort of like a forward prediction. We do backward updating, and if we can modify the model, refine the model, and then that makes this mathematical model a digital twin. Now, the problem is the finite elements method are not developed for the back calculation. They are developed for the forward calculation. So you need people like me, university researchers, and to develop the mathematical means. How can we do this kind of back propagation to deal with that challenge? And the approach we take is we replace some part of the finite element model with machine learning. And there's a lot to talk about that, but I won't get into detail of that. So we replace part of basically the material behavior, the material model part of the finite element model. We replace that with the machine learning. We are not replacing the entire finite element model with machine learning. We only replace part of that. So we are integrating machine learning with finite element model. So that's what our approach. And what that does is that allow us to do this back propagation, that allow us to update the mathematical model. So once we have data from the manufacturing process, we can refine the mathematical model, and then we do forward prediction, and that can help us to do the process control. So that is the general methodology. The other thing I want to mention is that if you are familiar with finite element simulation, I'm sure a lot of you are, you would know that there are a lot of things it's very difficult to input a lot of parameters into finite element analysis. For example, if you have chemistry data, you have chemistry composition data, you have microstructure, sometimes you have microstructure data, you have processing data, you might have processing temperature changes. All these things are difficult to be taken as input in the finite element model because the finite element model, by definition, is a mechanical model. But by integrating machine learning, a machine learning part, integrating that with the finite model, it is possible. It opens the door to take input of all those difficult parameters in the finite element simulation. So this is a very, very general approach. It's not limited to sintering processing of ceramics at all. It is general approach for any manufacturing process that can be simulated by finite element analysis. So what we're doing, we develop what we call neural constitutive law, which is basically the material model. And again, I don't have time to talk about the details. So we have a simple an architecture. We have input, microstructure, grain size, density, mean stress, effect stress. Again, I don't have time to talk about that. And we want output like grain growth rate, derivative strength rate, and volumetric strength. These are. If you are familiar with finite element method, you know what I'm talking about. But don't worry if you don't know. This is just a material model. So we put that in. Then we do a two-step training. This is the challenge because once you have a material model using the machine learning, you have the challenge of training it. And then, as we know, training and always demand for a huge amount of data. So to deal with that challenge, we are using this two-step training approach. So initially,
30 seconds left. That's right.
Yeah. Initially, we train the model by a mathematical theory, and then we retrain it using manufacturing data. So that's a two-step training data, and then we can retrain it whenever you want with whenever data is available. So that makes the digital twin. So I'm going to talk. I'm not going to talk about this. So we pick up a mathematical model, and then we have some experimental data, and we train it and we retrain it. And so first time when you just train it using ANN, so this is a finite element analysis with ANN at each center. And this is, as far as I'm aware, this is the first time ever people have done this in the academic community. Nobody has done this before. And then we can retrain it using further experimental data. And again, I'm running out of time, but basically I'm showing you that you can have FEM integrated with ANN and run it, train it by mathematical equation, give you a validation, and then you retrain it using real experimental data tell you something new which you didn't know. And this becomes the cornerstone, the fundamental methodology for our digital twin. And we are developing this for real product with our collaborators, Lucidin, Morgan, and Rolls-Royce, and we have 3 separate projects each working on a different product manufacturing line. The work is published. The academic part of the work is already published, so you can get that by this. And we are funded by, as I said, UKRI, and the whole consortium we have called Midland Advanced Ceramics for Industry 4.0. We got the government gave us 18 million it's a 5-year project. We are halfway through, and the digital twin part, I'm leading it. We have 2 million budget for the project.